we're now ready to think about independence. So remember our experiment where we rolled the die twice, and A was the event that we got a 6 on the first roll, B was the event that we got a 6 in the second roll, and C was the event that the sum of the observed numbers was 11. And remember we had the probability of A is equal to the probability of B, which is 1 over 6, and the probability of C was much smaller. It was 2 over 36. And then we calculated the probability that B would happen, given that A had happened. The probability of getting a 6 on the second, given that we had a 6 on the first, is 1 over 6. And that was also equal to the probability that the sum was 11, given that the first number was a 6. Notice that the probability of getting a 6 on the second, given we got a 6 on the first, is exactly the same as the probability of getting a 6 on the second. The underlying condition that we got a 6 on the first has no influence whatsoever on the probability of B, on the probability of getting a 6 on the second. On the other hand, the probability of that the sum of the two numbers is 11 is increased given that we got a 6 on the first. So the probability of C given A is bigger than the overall probability of getting a sum of 11. Since 11 is a high sum, the highest sum we could get is 12, this is something we might expect, that getting a 6 on the first would increase our chances of getting a large sum for the two numbers. When the probability of an event B doesn't change with prior information or an underlying condition A, or given that A has happened, we say the events A and B are independent. So above we have A and B are independent events, and A and C are not independent because the underlying condition A changes the probability that C will happen. Here's the formal definition. We say two events A and B where the probability of B is not 0 are independent if the probability of A given B equals the probability of A. So this amounts to saying the fact that B has happened or is guaranteed to happen doesn't change the probability that A will happen. Since the probability of A given B is the probability of A intersection B divided by the probability of B, assuming that the probability of B is not 0, we're never allowed to divide by 0, saying that A and B are independent is the same as saying that the probability of A is equal to the probability of A intersection B divided by the probability of B. And if I multiply across by the probability of B, that's equivalent to saying that the probability of A intersection B is the product of the probabilities of A and B. So from this, we can deduce that if the probability of A given B is the probability of A, we must have the probability of A intersection B is the product of the probabilities, and therefore the probability of B is equal to the probability of A intersection B, the product of the probabilities, divided by the probability of A, which by definition is the probability of B given A. So it's a perfectly symmetric definition. If A and B are independent, then B and A are independent, and we don't need to worry about the symmetry. If any of these formulas hold, since all three are equivalent, we can conclude that the two events are independent, and vice versa. If we know or assume two events are independent, then all three of these formulas hold. Okay, let's look at an example. If I roll a die twice, and A is the event that I get a 6 in the first, and D is the event that the sum of the numbers is 7. Are A and D independent? Now this is a little harder to judge. We'd expect that a 6 in the first would increase our chances of getting a high sum, but 7, somewhere there in the middle, so we're not exactly sure if getting a 6 in the first changes our probability that the sum is 7. So let's check using conditional probability. So we have 6 outcomes in A and 6 outcomes in D. I've listed them. And A intersection D has exactly one outcome, a 6 on the first, and then the sum is 7, so the second observation must be a 1. So our question about whether these two events are independent can be translated to the following. Is the probability of A intersection D equal to the probability of A times the probability of D? This is one of the 3 possible translations of the question that we saw on the last slide. So what I'm asking is 1 over 36, the probability of A intersection D, equal to 1 over 6 times 1 over 6? And you probably have the answer. The answer to that is yes. So therefore the answer to the previous question is yes. Yes, A and D are independent events. We also have the concept of many independent events. If I have several events, E1, E2, down as far as En, that n could be 100, it could be 5. They're independent if the probability that any subcollection of them happens at the same time is the product of the probabilities of that subcollection. Of course, this means that the probability that they all happen at the same time has to be equal to the product of the probabilities of each event. Now this amounts to saying that the probability that the nth event happens doesn't depend in any way on any combination of the other events happening, or whatever combination of the other events has already happened. For example, and here I'm going to assume independence. I'm rolling a 6-sided die 3 times, so I wouldn't expect what happens on the third roll to be influenced in any way by what has happened on the previous 2 rolls. So if I roll this 6-sided die 3 times, the probability of getting a 6 on the first, a 6 on the second, and something less than a 6 on the third should be the probability, since these are 3 independent events, the probability of a 6 on the first times the probability of a 6 on the second times the probability of something less than a 6 on the third, which is 1 over 6 times 1 over 6 times 5 over 6, which is 5 over 216. So independence is a double-edged sword. Here I'm assuming independence and applying the formula. In the previous example, I was checking independence by checking the formula. In this case, we're assuming the independence and we're applying the resulting formula.